So all this is to really say that the notion of finite state automaton is very robust, right? It's equivalent to many different notions, and so in the theory of computation, there are two classes of machines that we talk about: finite state machines, and of course infinite state machines, represented by Turing machines. The idea is that these two are robust classes. That robust classes in the sense that you can do all sorts of things with it. You can change the definition in 100 ways, and it comes out to be the same. The behaviors are the same. That's the spirit of this equivalence theorem. And similarly, with Turing machines as well, but the sense of Church-Turing thesis, you can do pretty much anything with it, change the motion, all sorts of ways, but the class of functions computed is exactly the same. So these are cornerstones for theory of computation. And of course, there is a large gap in between the two, between finite state and Turing machines, which is largely an area of darkness, and a lot of research is on it. But that's theory of computation and the story there. Here, what is of interest is that of, as I said, logical definability as a notion that links all these together, in a beautiful way. And maybe towards the end, I can talk about why that takes you further. So what are words and languages? So in general, the set of words satisfying some properties is what you call a language, just a subset of words. And a word is simply a finite sequence of sigma, which is a finite alphabet. For instance, these are all examples of regular language. Spelling mistake again. Every occurrence of A is eventually followed by B. So take the set of all strings over A and B, where you make sure that or A, B, C, let's say, right? So every A is eventually followed by a B, so that it should never be possible that you take a string where it ends with just a sequence of A's, right? And so that's not acceptable. And there is exactly one A, like all sequences where first letter is an A, last letter is an A. Every occurrence of A is immediately followed by a B. This is different from that, right? Here, what you're saying is that the moment you see an A, you can't have a C in between, right? It must, what you see immediately next is AB. So it's AB, 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 with lots of C's probably interleaved if you had C's. And then here is one which says that even number of A's, there are an even number of A's in the string, except all the strings there. So these are all you can think of as specifications. And what we can show, again, elementary exercise at the beginning of automata theory that you learn, that you can build automata. On the other hand, a set of words which satisfy the property that there are an equal number of A's and B's. Right? So you accept the language contains all those strings where the number of A's must be equal to the number of B's. This is not a regular language and is not acceptable. It's not recognizable by any finite state automaton. And again, you learn techniques in theory of computation to prove results of this kind. And yeah, so let me not get into these things. Now, all these words, all these languages, you can try to give descriptions in first order logic. How would you describe these in first order logic? For instance, the first one, every occurrence of A is eventually followed by B. I write it as something like this. For all x, PA of x says, now what are x here? I'm looking at a string, right? A string, what is a string or a word? It's a linear order, finite linear order, where every element of the linear order is labeled by some A. Let me fix it to be A and B in the alphabet. Right? So the first one says, if I look at any position, if that position is labeled by an A, right, that's a unary predicate. If the position X is labeled by an A, then there exists a position Y, which comes later, Y is greater than X, and that position y is labeled by a b. Right? So you can use monadic predicates PA, PB, etc. So for every element of the alphabet, sigma, I have a monadic predicate. Right? So if you have sigma has letters A, B, C, I have three monadic predicates PA, PB, PC. Right? And the length of the word is unknown. It's a finite word, but you don't know. And so your positions in the word are denoted by letters, X, Y, etc. denote positions, and you are talking about this. And then you have the ordering. So you can look at the first order theory of linear order. So that means the language is of order, where I have unary predicates corresponding to labels. So I can describe finite linear orders using this language.
Sir,
Yeah.
what is monadic?
Don't worry about it. Unary predicate. It's just, monadic, dyadic, triadic is a term. For dyadic means binary, and triadic means ternary.
Okay, sir.
Yeah. Yeah, it's fine. And it's just that I'm used to the terminology. Yeah. So what does this say? This says there exists X such that PA of X holds. Means some letter is labeled A, and for all Y, if the position Y is labeled by A, then X must be the same as Y. So this is precisely our there is exactly one A, right? This is, there is some position labeled by A, and if you take the contrapositive of this, it is not the case that you can find a Y such that X is not equal to Y and PA of Y, right? You can't find one more, there is exactly one A. And then the first letter is an A, last letter is an A. So this is saying that for all X, if X is the first letter, for all Y X less than or equal to Y says X is the first letter, first position, and it's labeled by A. This says that if X is the last position, it is labeled by A. What about this? This says that for all X, right, if X is labeled by A, then the immediate successor of the recent successor Y, which is labeled by. Here it's not individual, eventually, here it is successor. Now, of course, successor, you don't have it in the language, but you can define, right? Sxy is what? X is less than Y. And for all Z, if X is less than Z and Z is less than Y, X is equal to Z or Y is equal to Z. Yeah. On the other hand, what about the last predicate that we were talking about? There are an even number of A's. Well, last class, I went through all the rigmarole to precisely show, using EF games, that in the first order theory of linear order, you cannot describe having even number of A's. Evenness is not F4 definable. It is. So here already, we know that evenness is not F4 definable. Even if you put labels, it doesn't matter. You can take the same EF game and show that parity is not definable, and that it's regular is something that, again, it's an elementary exercise in theory of computation. So it already tells you that if you want to describe finite state automata, first order logic is not going to be enough. You do want to describe theory of sequences, it's going to be a logic of sequences, but it's first order, it's not first order. And so if you are after capturing regularity, clearly FO is not expressive enough, right? You can't work with first order logic. Basically, we know that FO cannot count, right? Even evenness cannot be expressed. In fact, 0 mod k for any k is not expressible in first order logic. And whereas that's precisely what finite state automata are good at. They can count, there's only bounded counting. In fact, what they do is modular arithmetic, but this is something F4 cannot do. So we need to strengthen first order logic somehow. Right? So you have to add something to first order logic. And what can we do? We add more quantifiers, more connectives. If you add quantifiers, what kind of quantifiers we do? Right? We have had for all x, there exists x, right? Some x, all x, that's all. Well, there exists unique x, but that's already expressible. What about count x? Suppose you want to add something like the number of uh, elements that satisfy the property, right? Instead of saying for all x px, you want to say number of x satisfying number of x alpha x greater than 5, right? But that's already expressible with a longer sentence in first order, right? I mean, how do you say number of x alpha x greater than 5? You say there exists x1, there exists x2, blah, 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 not equal. Yeah? What about, and you can go on like this, right? So unless you go for binary quantifiers, right? Pretty much most of these things that you can look at, you can play around just with the logic and so on. One possibility is to, for instance, add not quantifiers, right? For instance, I say number of x such that alpha x is equal to 0 mod k, right? You can't say that, right? Now that you can't write in first order logic or an arbitrary k. But this really means that you will need to add one mod k quantifier for each k. I'm not afraid of it, you can do that. But yeah, so that's one. What about extending the vocabulary? Right? We have only order. We have positions, we have order. You can only say x less than y, right? What if I can do arithmetic on x and y? For instance, suppose you add the addition function. Oh, there is for all y here. Yeah. Suppose I write there exists x such that for all y, y less than x. So what is this talking about? So there is an x such that to the left of x, right? There is a position x for all y less than x. That means to the left of all there are a's. And then for all y that is x is less than or equal to y. That means all positions to the right of x. There should be b's. Yeah. So and then x plus x equals last. Now this is just an abbreviation. How do I write x plus x equals last? There is no element called last. I really have to write there exists z such that x plus x equals z, and for all z prime for all y, y is less than or equal to z. That's an easy way. This is basically the language a to the n, b to the n. And why is this the language a to the n, b to the n? You're talking about a middle element. Okay. Until then, it's all A's. After which, it's all B's. Right? If I correct it here, and this says that that number is exactly equal. Should just check whether it's less than or equal to or not. One of these, basically. Yeah. And as I said, in theory of computation, one of the things that you show is that this language is not regular. Like the language with equal number of A's and B's, a to the n, b to the n is also not regular. So adding addition is one possibility, but it takes you too far. So, and but then last time I talked about implicitly definable functions. One of the things I talked about was having, let's say, a predicate p, unary predicate, in which suppose you could write, and what I showed was this was something implicitly definable, but not explicitly definable. And therefore, in fact, the definability theorem fails for finite models. And one of the points that was talked about last time was that you can write, consider predicate P, unary predicate. It satisfies P min. That means what? A minimal element belongs to P, right? And whenever you consider Y successor of X, P of x holds if and only if negation P of y holds. That means what? P holds for the first element. It doesn't hold for the second element. It holds for the third element. It doesn't hold for the fourth element. Do you see what's going on? That means it holds exactly for the odd positions, right? If this were explicitly definable, parity would be definable. But then we use EF games to show that parity is not definable. Therefore, we show that this is not explicitly definable in first order logic. So add such a predicate. That's it, right? So one very simple way of adding that is to use, so if you could refer to sets of elements, you could actually express this. So for instance, let me say that there is a set of elements X such that min is sitting inside X, and whenever Y is a successor of X, the set X contains X if and only if it doesn't contain Y, right? So this ensures that min is there, min plus 1 is not there, min plus 2 is there, min plus 3 is not there, min plus 4 is there, and so on, right? So if you start counting from 0, this defines evenness. If you start counting from 1, it can, captures oddness. So basically, this is the monadic or the unary predicate second order extension of FO. That's why it's called monadic second order logic. So basically, it's an extension of FO with not only quantification over elements, but over sets of elements. So in general, you have a domain, and your quantifiers refer to elements of the domain. There is an element for all elements, etc. And now, in addition, we are adding set quantification. And so what is the logic that we are working? Any questions until this point? Okay. So what is the syntax of the logic? Well, fix a finite alphabet sigma. And the language has vocabulary, no constraints, no function symbols. You have the order predicate, the order boundary relation, and for every element A, you have a unary predicate PA, right? So intention is this is going to talk about the set of all elements that are labeled A, right? And we have two sets of variables, first order variables and second order variables. And I'll use normal x, y, etc. for first order variables and uppercase x, y, etc. for set variables. What is the syntax of formulas? Well, this is a monadic logic, means that there are only unary predicates. I don't add any general arbitrary unary relations at all. I have only unary predicates. And these are unary predicates that come along with some labeling of. So for every element, there are one, and that's all. The only binary relation is x less than y. And of course, you have equality, you have membership, because now you have sets of elements, and then negation, disjunction, then you get all the Boolean connectors. There exists x, which is the standard quantifier, and then there is a set quantifier. And of course, you define for all x by taking not there exists x not. Similarly, you have for all sets of elements. And I don't need to do anything more because I can define what about set equality, but that can always be defined because x is included in y if and only for all x, little x belongs to x implies little x belongs to y. That defines inclusion. Once you have inclusion, so you have second order equality also available in the logic. And so this is what is called the pure predicate calculus in general. No constants, no function symbols, and we have even come down further that I'm not even having binary relations. Right? There is only one fixed binary relation, no uninterpreted n relations. Yeah. So the only uninterpreted relations that are available to you are unary. So it's monadic in this sense. Is the syntax clear? Okay. Now let's get to the semantics of the logic. Now, what is this? We want words over sigma. to be our structures. So with each word W of sigma star, say let's say A1 to AN, we associate first this MSO structure, no, not first order structure, as follows. What is that? So let me call it W bar. W bar has domain 1 to N. So remember, N is the length of the string. So for that string, the positions are 1 to N. And N greater than or equal to 0. So in particular, if N is 0, this is the empty string. This is the empty domain as well. And then you have an order relation. This is the standard ordering of numbers. And then PA. So the interpretation for the unary predicates PA. That's all we need, right? And what is that? And this is nothing but the set of all, the interpretation for PA is the set of all J, right? You go out here, find all the positions where A actually occurs, right? So collect them, and that's the set, that's the interpretation. That's a subset of the domain. Yeah? And so your unary predicates are to be interpreted as subsets of the domain, and that's what you've got. Now, in general, when you have a formula alpha, let's say that, in fact, it may not be equal to, I can put subset here, but say these are the variables occurring free in alpha. So these are the first order variables occurring free in alpha, and these are the second order variables occurring in alpha. This should be big X, yeah, X1 to X. Yeah? Then I can define, you take the structure, the interpretation of the second order variables, them sets, and the first order variables. One of them is M and N. Fix it as. Yeah. And how do you define this? This is as usual. Clearly, the predicate symbols, the interpretation is already given, right? X equal to Y, well, it's obvious. If whatever xi equals xj, if you have ai equals aj, and then the membership xj belongs to xi if and only if the corresponding aj belongs to corresponding ai, right? So the interpretation is all given on the left-hand side. Right? This is the sequence notation that I was using earlier, instead of writing pi. And what about the existential quantifier that we have added? There exists xi alpha if and only for some b subset of n. Look at the variant model, which is go over to the same thing up to ai minus 1, substitute b here, and keep all the rest the same. This satisfies alpha. I'm sorry. This is again a cut and paste. Yeah? So it's to say that it's exactly the same thing that we would expect, like in first order logic. So we have just lifted whatever is the semantics that we had for first order logic to add set quantifiers. Right? So it's fairly routine. What is very interesting is what we get out of it. Now, as usual, what is the sentence? It's a formula with no free variables. And now, if you have a sentence, given any word, you can now talk about W bar satisfying the sentence, right? Because there are no free variables, so there is no extra stuff at all. So in general, you can actually say that the language of the sentence is the set of all words such that the associated structure satisfies the sentence. So this is what we usually call mod phi, right? Mod phi is now a language. And so in this sense, you take a sentence of this particular logic, whether it's FO or MSO, you can associate a language with it. Now we say that a language L subset of sigma star is MSO sigma definable if there exists a sentence in MSO sigma such that the language of phi is exactly equal to it. And this is how we have talked about all these things, right? We say a class of structures is definable if there is a sentence such that the models of that sentence is exactly that class. Instead of the class of structures, now a structure is a word, so it's a set of structures and then it's a language. Now we can similarly speak of L being FO definable, right? Where you don't use set quantifiers at all, right? There is a first order fragment sitting there, and you can talk about language being first order definable. So, and comes the main theorem. as mentioned earlier, MSO definability gives us yet another way of understanding regularity. The theorem Buchy, Elgot, Trachtenbrot, actually it was first proved by Buchy in 1960, independently proved by Elgot in 1961, Trachtenbrot in 1962, different notations, different variants, but it amounts to basically this, that L is recognizable by a finite state automaton if and only if it is MSO defined. And so L is recognizable if and only if it is regular, if and only if it is rational, if and only if it is MSO defined. So, it brings all these things together very nicely into one. And now, of course, you can ask, what about L being FO defined? And this is the theorem of Chauvet-Berger in 1965, where proved that L is star free if and only if it is FO defined. You know what I'm talking about. Again, Siddharth, have you seen star-free languages?
Yes, sir.
Okay. So, have you seen this theorem before? Or?
Yes, sir. Like it came up, but we haven't given the proof.
Yeah, the proof is more complicated, and maybe I can take it up later if anybody wants. But that we need to go into the algebraic machinery. We have to look at the syntactic monoid, aperiodic monoids, and so on. And that is the root. But it's at least to know that L is regular if and only if MSO. So now FO is a fragment. What is a corresponding fragment? It's exactly the star free. Yeah. And so basically what we are left with is proof of these theorems. As I said, this one is a little bit, take us too far probably. But this one I can do a proof. And let me take up the proof right now. Okay. So before I start on the proof, any questions? Okay. I just got this, so I don't know how well I'm going to use it. So let me try. Use this whiteboard and connect. I hope it works. Yeah. Okay. Yeah. So what is it that we want to do? We want to show that if oops, stop this in a moment. Okay. Yeah, what I'm going to write is if this goodness. It's told that I just have to write on this. That, okay, let me try this. Yeah. Just one moment. I'll try again. Okay. So start writing. Let's see. Is recognizable implies. Okay. Now we have an automaton sitting here, right? So you have some units. You have so let me call this machine A. Where does it keep going? Okay. So how are we going to, how do I describe what the machine does, right? What does it mean to say W belongs to language A? That means that there is a run. So let's say W equals A1, A2, up to AN, right? Now, I'm assuming a deterministic automaton. So, but that doesn't really matter. So, or if it's a non-deterministic automaton, I have, yeah. So let me in fact assume that I have a non-deterministic machine. So you have a finite bunch of, so this is in fact simpler, right? So let's assume that L is recognizable. And so what does it mean? There is a bunch of states. So these are the initial states. These are the final states. And there is a path from one of the initial states to one of the final states via W, right? This is what it means for a word W to be accepted by the automaton. So that means I should be able to find a path on A1, automaton goes from Q0 to Q1, on A2 to Q2, and so on. On AN, it goes to Qn plus 1, such that this belongs to F. And this belongs to I. So you start from one of the initial states, and there is a path on A1, the automaton can make a transition to Q1, to Q2, and so on, and you arrive at F. So this is really what your automaton is doing, right? Now, how do I describe that in terms of logic, right? Now I have positions 1, 2, up to N. Up to N. Now, you know that this one is going to be labeled by some Q0 belonging to I. And from this, automaton goes to a state Q1. And then it reads A2. So this is labeled A1. This is labeled A2, and so on. So you keep going like this. So at some point, you're going to, yeah. So you will get Qn minus 1, some Qn. This should be Qn. Yeah. And this belongs to F. So this is the process that you want to describe logically. You have a structure, 1 to n. They're all labeled appropriately by letters, right? If I call this X, the first letter is labeled A1, second letter is labeled A2, and so on, up to AN. But in addition, I'm going to have a labeling of the letters by states. Yeah. There are n states in the automaton. Now, how do I say this state is labeled by Q0, Q1, Q2? Well, we are talking with a logic which has set quantification. So what we can do, use, okay, I have how many states? Well, this is a finite state automaton. So Q is of size K, let's say, right? Then I have states Q1 to Qk, and I want to say, which are all the positions where Q1 occurs, which are all the positions where Q2 occurs, which are all. Now that is easily done by set variables. So this is what we do. So now let me find the way to clear. Yeah, clear out slide. Yeah. And I start again. So now this is what I'm looking for. 1, 2, n. And this is labeled A1, this is labeled A2, up to n. And now I have state labelings. So what I do is, if, well, instead of calling it Q1, there is really no reason why I cannot call them simply 1 to k. There are some k are k states. I just call them 1 to k, right? There is no problem with that. So, and now I use x1 as the variable x1 to talk about set of positions where Q1 occurs, x2 to be the set of positions where Q2 occurs, and so on, xk as the set of positions where the state Qk occurs, right? So now I can completely describe the run of the automaton on the word A1 to AN, right? So I can write, there exists x1, there exists x2, there exists xk, such that, now I have to write certain conditions. I have to make sure that if a position is labeled by a state Q1, it is also not labeled by a position Q2, right? Basically, the x1 to xk partition 1 to n. I have to write this, right? Because if I take this as the set of positions where x1 is the set of positions where q1 occurs, q2 occurs, and so on, the union of all of them has to be 1 to n, and they have to be disjoint. Is this clear? Yeah. So they have to form a partition. So this ensures that labeling is correct, and then I have to ensure that whatever is, the min position has q belonging to I, right? The initial position is labeled by something in the initial state, one of the initial states. What is an automata? Q delta I f. Yeah, and then I have to say, remember how my transitions go. The last transition takes me into F, and I have to say that whenever S, right, if I am in a, so basically when I consider I, A, J belonging to delta, right, I am really talking about X in Xi, Y in Xj, right? The consecutive positions are labeled by the transitions and PA of X. Yeah. This ensures that when I'm sitting at any particular place, that position is labeled by A, and the transition is from I to J. Right? That's what. If I can somehow write formulas for writing all these things, I can describe a run of the automata. Is the strategy clear? Basically, a path from I to F in the graph of the automaton, right, tiled by triples of the form Qi, A, Qj, Qj, A, Qj prime, etc. And that's exactly what we are writing. So you have to write formulas for all of these. And once you have this, it completely describes that this is a word accepted by the given automaton. And so how do we write formulas for doing these things? And so that is the next thing. Okay. Clear? So let's keep in mind our Q is 1 to K, and the automaton is Q delta IF. And I have now the formula. There exists x1, there exists x2, there exists xk. Now, how do I write that they form the excised form a partition? How do I say that?
Pairwise empty intersection.
Yes. How do I write that?
So for all I not equal to j implies intersection of xi and xj is empty.
And over I not equal to j. We don't need, this is just a finite one, right? So I don't need quantifier. So I have to write for all x belongs to xi, if and only if, right? This is its pairwise empty, and for all x, or over I equals 1 to k. Yeah. This ensures that they form a partition. Every position is in one of the sets. And is this clear? And since this is our intention for talking about state labeling, you are saying that the automaton visits, it's in exactly one state at any point of time. Right? Your automaton is not in two states or two or more states at any given point of time, and it's always in one state, some state at the end. So this part is clear. And then or over I belonging to I, xi belongs to min. Sorry, I should write something better than this.
Thank you.
Yeah. So you want to say that you are in the initial states, right? I is an initial state. So how do I say that? Yeah. Again, I'm using min. There is no such thing in the language. I have to write there exists z such that z belongs to x1, xi, and for all y is less than or equal to z, and greater than or equal to z. Right? So this says that the minimum position is labeled by one of the initial states. Yeah? And over I, A, J belonging to delta, take any such transition. And what do you want to say? We want to say that if you are in if x belongs to xi, right, and the automaton is reading the letter PA of X, and successor of X, Y implies Y belongs to Xj. Yeah. And of course, you have a for all X, etc. I have to write for all X, for all. Yeah. For all X, if you take any pair of positions, if a position X is in state I and reading the letter A, right, and the next successor is Y, then Y is in one of the states given by XG. That's actually in particular state XG. So this says that my word is actually, the run is tiled by triples given by the transition function. And then I have to write R over J belongs to F. I, A, J belongs to delta. So this is transitions that take you into the last state, right? So basically I want to say, X belongs to Xi. Actually, I don't have to write. I just have to say last. Yeah. I have to write. Last Y. X. Yeah. Yeah. That may be a simpler coding. I just have to make sure that when I read the last letter, what I land up is in one of the final states. Yeah. So this is now so this completely describes a run of the automata, right? Is it clear that Y belongs to Xg? Yeah. I've just rewritten this here as a conjunction, except that I am now taking this over IAJ in delta, where J actually is transiting into the final stage. One of them will actually be. Yeah. And again, these are for all X for all. Now we have to show that this sentence phi, the language of phi is actually equal to the language of the automata. And this is a fairly routine induction on, because suppose you have a structure that makes the sentence true, look at the associated word, and we have to argue that word is accepted by the automata. And for that, simply go through the meaning of all the components that we have got. This is basically a saying that the coding that I have done is actually correct, and it actually leads to a string accepted by the automata. And the converse is also. This proof is completely straightforward. It's a routine induction on the length of the word, right? Take any model of the sentence, that will give you n, and now do induction of it, right? To show that it is accepted. Yeah. And similarly for W belonging to sigma star, so there is a bijection between the words accepted by the automaton and the runs specified by the formula. And so every run will give you a model, and every model gives you a run, and that's it. Okay. So this says that every recognizable language is MSO defined. Is it clear? Proof is fairly straightforward. And note that there is something interesting in this in terms of the tightness of code. First thing is that, first observation is I have used K set quantifiers, right? Do you need, say, K set quantifiers? I've already said you don't need. So, of course, you don't. So, how many set quantifiers do you actually need? Anybody? Anyone would like to guess? Yes, Siddharth?
Sir, the number of reachable states.
Well, okay. Yeah, but that is order K, right? So not that much fun. Okay, here is an exercise to think about. Show that you can do it with order log K quantifiers, right? Because I just need to represent that state, right? I don't have to name the state, right? Log K bits are enough to say which state I am in. Yeah. Of course, the coding has to be a bit more clever, and you have to, be more careful in the formulas you write. I am writing in a very generous and expensive fashion. Yeah. So if you have to think about, logical resources, it's a good idea too. Yeah. But it seems reasonable, right? Siddharth, you understand the point of what I'm saying. Yeah. So it is possible, and try to do it. Yeah. So you can do with log K quantifiers. So that's one remark. Another remark is that actually nothing in this, right, says that the automaton has to be exactly in one state at the same time, right? If there is a notion of a run, right, where you could build machines where the automaton could be in two states at the same time, right? The coding will go through. You just have to knock off that one portion out there. The tiling, all the logical form, the structure of the coding in the logic is not dependent on that at all. Do you see what I'm saying? It hardly matters for the coding. That's the beauty of set quantification that you have, right? You can have positions multiple by, have labeled by multiple states, right? So there is a model where you go into quantum finite state automata, and the MSO coding goes through exactly the same. Of course, there's a lot more work to talk about the words accepted by the automaton. I mean, for the machine theory itself, there is a lot of work involved. My point is that if you know what it means and can aggregate your semantics right, the logic coding is completely straightforward. Right? You will find that in the context of Turing machine coding as well. The logical descriptions are very abstract, and you can play around with it a lot. For instance, all the superposition and so on is no problem at all. You can go to quantum Turing machines, you can have the coding going through the same way. So there is a lot here that's hidden here. Like I said, I am doing the coding for non-deterministic automata, right? Now, one of the theorems is that every language is accepted by a non-deterministic automaton if and only if it is accepted by a deterministic, right? Where we use the subset construction, and if you get that. When you see it in terms of logic, you find that the formulas look almost the same. So what's going on, right? So you can think about, so the logical description will give you the most abstract description you can think of. It doesn't matter for whatever class of languages you look at. And so there is actually, it's a very simple idea, but it bears a lot of analysis, a lot of generalizations. So this direction is always the easier and nice one to work with. What about the other direction? You need to show. Yeah. Now, yeah, I want to prove that L is so definable implies L is recognizable. Yeah. And now I'm going to use the fact that, I'm allowed NFAs, non-deterministic automata, because it's, the construction is going to be wildly non-deterministic. So that you've not seen a proof of this, right? Okay. So this is non-trivial because you've got a formula, right? This formula does not have any structure, like X representing states. We know nothing, right? It just is something about sets of positions. It's got some relation between positions, something labeled. That's all. It doesn't say anything. Somehow from that, I have to build a finite state of form, right? How do I hope to do that? So this is going to be by induction on the structure of the formula. Yeah. Yeah. That makes sense. The only problem is, right in the atomic case, we have a problem. Why? Because we said if I'm going to do induction, I need to use the induction hypothesis, right? Forget the atomic case. Start with the, if you're given a formula not alpha, right? Well, what do you have by induction hypothesis? Not alpha, not phi, right? You have, with not phi, you've shown it's, I want to show the language is recognizable. How do I do that? By induction hypothesis, there is an automaton for phi. Right? Take the language, complement it. You know that regular languages are closed under complementation. Do you see the point? If alpha is of the form not beta, right? The language of beta, there is an automaton A. Right? Now consider A prime that accepts the language of A complement. Right? This language is not beta. Is it clear? If somehow you can get past the atomic formulas, right, you can start doing induction by using closure properties of regular languages. The recognizable languages are closed under complement, so that takes care of negation. What if alpha is beta 1 and beta 2? By induction hypothesis, the models of beta 1 recognized by some automaton A1. This will give you some automaton A2. But we know that there exists an automaton A. This is the intersection, right? The language of A is language of A1, intersection language of A2. So this is in fact the language of phi or alpha here. Yeah. Recognizable languages are closed under intersection, and we are done. Am I making sense? The fact that recognizable languages are closed under Boolean operations tells you that the Boolean connectors will lift neatly. What about alpha is of the form Oops. There exists X beta. Well, for beta, I've got a language, some automata. Now, I want to go in every run, look at some particular position X, right? And I want to say, I want to project it down, right? And consider the formula alpha. But that's basically the notion of homomorphism, alphabetic homomorphism, and recognizable languages are closed under homomorphism as well. So there are enough theorems to closure properties of recognizable languages that lift you the whole thing. Problem is with atomic formulas. Atomic formulas are coming with free variables. Now, my automata are available only if you are looking at sentences. So already we have a problem. So somehow, rather than talking about definability over sentences, I have to go to definability over words or over formulas. This is a non-trivial point. Does everyone understand what I'm saying? Not clear? I said with a word you associate a structure. Now that structure is true, a sentence is true or false in a structure. But if I have a formula, I have to have assignment to free variables, right? So your formulas are going to come like this. So your formulas are, if I have a formula alpha, it has some free variables x1 to xm, and first order variables x1 to xm, and second order variable xm. A model for this is a word 1 to n. It's true that it's going to be positions are labeled by letters, and now we have already decided that they are also going to be labeled by states. That's okay. There is no automaton given. Remember, we are going to build the automaton. Now, you have to have some evaluation of this x1 to xn, right? x1 may be in this position, x5 may be in this position, x17 may be in this position. Is this clear? This may not be, this position is not referred to by any variable, and so on. So your positions are actually labels. The assignment to first order variables are also labelings of 1 to n, except that they have a slightly different. And now similarly x1. x1 is collecting some positions. Let's say x1 is here and here. x3 is here. x5 is here. Right? So what is going on is you are now talking about words over not sigma star. So we are not looking at W belonging to sigma star, but W belonging to an extended alphabet. Sigma cross first order variable cross second order variables star. Is this clear? So the models that I'm going to look at are over a much larger alphabet. It's every letter is actually a triple, right? First component says which letter I have got. Second component says some free variable, right? Maybe there, right? It may be having one of these, right, or not. Right? So if there are m vectors, right? Now I have an m-bit vector here, or you can think of it as a again set, yeah. And so you need not have any of them, and the second order variable that it has in this position, or right. So actually, what I'm going to do is to have an m-bit vector. So I'm actually going to write it as. So let's write it as. So it's going to be a huge vector. So First, I have the label. Yeah, A1 to AN. And I have an m-bit vector. So let me call it V1 to Vn. And then I have an n-bit vector. So let me call it C1 to Cn. Yeah. So my sigma is going to be so the alphabet sigma prime that I'm building is sigma cross 0, 1 to the m Is this clear? What it says is, first I have a letter, and then look at the ith position here. If xi is, xi is getting the value this particular k, right? I'm looking at the kth position of the word. If xi equals k, that bit will be set to 1. All the rest will be set to 0. Yeah. And this one says, well, if that position belongs to xj, that bit will be set to 1, else it will be set to 0. So this captures the definition of the thing. So it's going to be a, m plus n plus whatever is the size of sigma. So that's going to be your answer. Yeah, is it clear? So this is your alphabet, and now the set of legal strings. What are legal strings? Well, A, comma, let me call it sigma, comma, rho. Yeah. So A1, 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 AK, sigma K, OK is legal. If, what is it that we want? For all I belonging to 1 to m. Remember, there are m first order variables. Yeah. There exists unique j such that sigma j of I equals 1. Why? Because now each of those first order variables should get exactly one of the positions. Is this clear? You can't have that variable xi being set to 1 in 2 different sigmas, right? It should not be in all zeros either. And that's it. For the other one, for the rows, it doesn't matter at all, right? Whatever sets you can have empty sets. You can have. So now, so let me call this legal sigma prime is the set of all legal strings over sigma prime, and this is a recognizable language, right? So it's very easy to see, to construct an automaton that checks whether, and the automaton is completely straightforward. If I can point here. So you start, and at any point of time, you
after I'm going to work,
check
I'm going to start
if
studying.
the ith position. So this checks for I. Xi equals 1. Immediately you go into the final state, and after that you accept any. So this is a non-deterministic automaton. It starts at the initial state. It accepts anything until xi equals 1. And the moment it sees xi equals 1, it's willing to accept anything after that. Right? So this So this ensures that xi is actually made 1 somewhere, and at least once. Yeah. So this checks for xi. Now you can build an automaton for each individual variables. You'll have m such automata. Take the intersection of all of them, and you will get the set of legal strings. So that ensures that the set of legal strings is recognizable. So now I will just build arbitrary automata, and I keep taking intersection with legal. Right? We know that recognizable languages are closed under intersection, and that is true. So this is one important bit that we need to do. And after that, now proving for atomic formulas and so on. Remember that these automata are non-deterministic. So you have a lot of freedom in constructing these formulas. So now I have to check whether PA of xi, right? What is the automaton for that? This is supposed to check that the xith position, right? Take the variable xi, whatever it evaluates to, that position is labeled by a. So how do I do that? I want to show that the language accepted by this, the models of this sentence is recognizable. Well, it's very easy to build an automaton to check that. What does it do? Well, the place where xi equals 1, it checks that supposing you've got a prime sequence of bits, right? So it says that the ith position is 1 and a prime equals a. And then it gets into a final state, after which it is checked. Yeah? This is all it. And this is intersected with legal. Now we know that the moment I take intersection with the automaton for legal, I know that will become 1 at exactly one position, right? The xi, and there you are checking that this is equal to a. Otherwise, it will not reach final state at all. It will be looping. So a string where it is not labeled by a is not going to be accepted. So this is the way of checking for. What is the next atomic formula? Xi equals xj. Automaton for that. So this is the power of non-determinism. Once you have non-deterministic automata, all you have to do is, again, same thing. So just check that xi equals 1 at the same place xj equals 1. Now you intersect with legal. Just make sure that xi equals xj, right? Both become 1 at exactly the same time. This is making sure that xi is made 1 exactly once. It's making sure that xj is becoming 1 exactly once. And you are saying that the transition is when both are 1. Otherwise, this is stuck in the initial, in a non-final state. What about xi less than xj? Well, you start any. Consider any string, any transition where xi equals 1. And then you have any transitions. Xj equals 1. Yeah. So this is that I keep walking along my input. Sometime I must see xi should be equal to 1. And again, I'm taking intersection with legal. Right? If I never see an xi, well, look at the intersection with legal that takes care of it. Right? Xi is going to become 1. It's a free variable. So at some point it will become 1. It gets some assignment. Xj gets some assignment. And we want to make sure that it's less than that. And this ensures that first you will see xi becoming 1 and then becoming xj becoming 1 because of the way the intersection with legal is. So that takes care of almost all the atomic formulas. there is one more left. What is that? And that is x belongs to xi. So let me consider this. Xi belongs to xj. And this is also fairly simple with the same token. So you start xi equals 1, and we have to make sure that, let me call it, it belongs to xj by saying that the jth bit of row equals 1. And that's it. The moment xi becomes 1, so this is intersection. We want to make sure that in the third component, this is exactly the one place where you check. Yeah. So this ensures that all the atomic formulas are giving you recognizable languages. Then you have closure under complementation, conjunct, intersection, that takes care of the Boolean cases. Now let's get to the quantifiers. Is it clear? I mean, it's this thing you have to, the most important thing is to get your coding of the structures very clearly, and after that, exploiting the power of non-determinism. So now all we have left are the quantifiers. So alpha is of the form there exists xi beta. Now for beta, consider any model. How is it going to look like? A1 through an, and then you have your bit string. So let's say 0, 1, 1, 0, 1. This is for the first order variables. And then you have second order variables, some bit string 1, 0, 1, 0, like that. Yeah. Now there exists xi beta. So at some point here, the ith, if I take the ith row, right, it's going to be a sequence of zeros. At one point, it will become 1 and 0. Yeah. This is how the models for beta are going to look, because xi occurs free in beta, right? Now, what are the kind of models that I'm looking for alpha? A1 to an, copy all the bit strings up to the ith, right? And then skip the ith row, so up to I minus 1, and then start with I plus 1. Yeah. And then the SV. Yeah. But this is, note that this is a map from sigma prime to sigma prime, right? Every letter here maps you from triples of the form A sigma rho to A sigma prime rho, right? That's what it is. So it's completely straightforward. You take the automaton for beta that is given, give the automaton A prime, where everything of the form, every transition of the form A sigma rho is replaced by a transition A sigma prime rho, where you simply delete the sigma prime equals sigma minus the ith element. That's it. This is an alphabetic projection, right? And we know that regular languages are closed under alphabetic projections, and this is all that is the proof that is needed. You take the automaton and simply throw out the ith row, look at the automaton A prime that you get, and L of A prime is exactly, yeah. And because if there is some word witnessing A, right, there is a particular element that makes, there is an ith row that makes it 1 somewhere. Now, this says there exists such an I, and so you move to one with fewer free variables, and it goes. Now you can check that all the models are done out correctly. So it's once again there. Now what about the second order quantifier? The proof is almost exactly the same. It's an alphabetic projection where on the second order projection, simply throw out the jth row. That's all. Yeah. And once again, regular languages. So, okay, if you complete the proof with all the details that I have said, now you have to prove, of course, that the resulting automata acts in the same language where there is a bit of reduction involved. But this completely tells you that this completes the proof of the Euclid. Now, there are certain remarks here that are relevant. Maybe I just write here. Well, I don't know to write. What's the size of the automata? Given alpha or given sentence phi, you construct an automaton for phi. Any guess? What's going on? For every atomic formula, you have an automaton. Yeah. Remember that intersection with legal you can always take at the end. So that will, that's not a problem. But every step you take. So how bad is it? Anyone else? Gayatri, how would you estimate the size of the automaton? The quantifiers only help. In terms of the size, they don't make any difference because we just apply erasure, right? Well, so how big is the automaton? And what are the operations being done? As I said, every atomic formula is going to generate an automaton. Okay, there are linearly many atomic formulas, linearly in the length of phi. So, if there are k subformulas, you've got k automata floating around. And then, what are the operations we do? Projection, as I said, doesn't change anything. You have then complementation and intersection. When you take two automata and intersect them, what happens to the new automata? How big is the new automata? Remember, these are NFAs, right? This is wildly not deterministic. So they are NFAs. So if I take instead of intersection, I could have been taking union. So that's not a problem. Yeah, maybe I take union because then you can just add two NFAs, size M1 and M2. I want something that accepts the union. What happens with complementation? I said you complement the automaton and that will give you the complement language. Yeah. So what does that give you? Yes, Siddharth? I take an NFA with M states and I complement it. What is the size of the complement automaton?
Exponential.
It's exponential. Exactly. So finally, if phi is a size, the length of phi is k, what is the size of the automaton? 2 power k, 2 power k squared, 2 power order k, what is your estimate?
2 power 2 power.
Yeah, so it's 2 power k, huh? Doubly exponential is what. I wish it were true. It's actually much worse. It's 2 power 2 power 2 power 2 power 2 power. 2 power k, where the height of the tower is bounded by the quantifier alternation. Every time, right, you had for all x there exists y, right? Remember, that is the same as a complement. Yeah. So you have, so every time I complement, I get 2 power n. And I complement that, I get 2 power n. And I complement that, right? Now, you can push negations, but you can't do anything about quantifiers, right? We just did the proof for existential quantifier. That's because you converted universal quantifier into existential quantifier also by negations, right? So you have to pay the price somewhere. And it turns out that it's actually non-elementary. That is the term that we use. So it's a height. So it's 2 power. Oops. It's 2 power, 2 power, 2 power, 2 power k, where the height is the quantifier alternation depth of C. Not quantifier depth, but quantifier alternation depth. Okay. If you have, what is a quantifier rank? You keep taking max, right? This is quantifier alternation depth. That means whenever you change quantifier, there exists, if you just have a sequence of there exists, there is no problem. If you have a sequence of for all, there is no problem. But the moment you have for all there exists, that's quantifier alternation 1. If I have for all there exists for all, that's going 2, and so on. Yeah. So, and there's a theorem by Mayer and Stockmayer, 1976, saying that this is in fact a lower bound. That means that this is not an accident of the wild way we were doing this, that in fact the size of the automaton that you construct is lower bound non-elementary. The term is non-elementary. So, so this is one of the, and in fact, even if you take a first order formula and apply this, you get an automata. Right? In fact, what I said is you can get a star free automata. But I'm afraid that's also not, and that's a lower bound. And so this is one of the, it's not an efficient construction by any means, but now comes the big mystery, because obviously when you have a non-elementary algorithm, no one tries to implement it, right? This proof by Bucchi, I said, is 1960. So this construction has been around for a very long time. So, and of course, 1976, there is a lower bound that became clear there's not something you actually mess with. But somebody decided to go ahead and implement it anyway, right? And in the 1980s, Niels Klarlund and his group in Denmark actually built Mona. It's called Mona. So Mona is a tool for monadic secondary logic, of course. And so it's a tool, and it's amazingly efficient. Okay, so this is one of the mysteries of worst case complexity, because it's easy to show that it's a non-elementary lower bound. And you can actually write formulas that force the tool to take a very long time. But in general, so today, in fact, Mona is used as an industry standard. Intel has its own tool which uses Mona. So what you do is Verilog in hardware circuits are all defined using Automata, and you want to verify. So the specifications are written in monadic second order logic, and you compile them into Automata and do the verification. And it turns out that you keep using the subset construction, right, at every time, so that it is. But then very rarely does the tool. So if you take not arbitrary automata, not arbitrary languages, but things that actually come from hardware circuits, right, represented as specifications and its automata, it turns out that substrate construction gives you very, very small automata in general, and you can write something in monadic subrouter logic and compile them into tools, and it, so this is yet another story of, don't ever give up on looking at lower bounds, right? When you start implementing, something happens that you're not prepared for at all. So Monas, as I said, not just a play tool, but actually is used as an industry standard. And now I believe there are 3-4 tools available now. Intel has its own tool, and Cadence has its own tool. So, I mean, I don't know how to explain these things. I'm just saying that such a thing happens, right? So, okay. So that's the proof of the Buchy-Elgort-Trachtenberg theorem, and so this is the Monad tool also that I mentioned. So I don't want to go too much into this. The other proof is much more interesting. I mean, it's, as I said, it goes through fair amount of good algebraic machinery. You have to look at syntactic monoids. You have to look at when they are group free and have first order representations of those. So that to prove that star free languages are exactly there for maybe we should take that up later on. This was only to show how extensions of first order logic are very natural and lead to natural connections in automata theory. But like I said, this is very rugged. When you go into new automaton models, right, automata that run on trees, right, automata that run on graphs, automata that run on partial orders, right, where, for instance, automata and partial orders, there are no good machines models available. But then you can very easily define monadic second order logic on partial orders, right? So in some cases, the machine model is more natural. You're looking at logical descriptions. Some cases, the logical description is completely straightforward. Now you ask, are there good machine models? And so there's a lot of such thing, and I think research progresses that way. Okay, you can build this game for context-free languages, context-sensitive languages. You can proceed this way for theory of computation. I don't want to go into that. This is only to show that this connection between logic and automata can be taken quite far. And it's almost always about closure properties of the appropriate class of behaviors. For concurrency, for instance, you can have concurrent models of computation with very nice, logical machinery and connectivity. Okay. So I don't want to go into that. This is just one shot to show. The other connection, which is very important, is with Turing machines, and maybe I should take that up next. Okay. Yeah. Thank you. Sorry I took long. Any questions? Okay then. Yeah. See you.
Yes, hello.